In this video, we're going to quickly derive a formula for computing arc length in polar coordinates, and then we're going to apply it to this rose curve and get the arc length of the curve. If you're not familiar with how to plot a rose curve, I'll post a link real quick to the video where this was first done. This particular one has the equation 4 cosine 2 theta, and you should notice in the example, I'm asking you to use a computer algebra system to approximate the arc length, and the reason why is that we end up with an integral we can't do analytically. So let's derive the arc length formula real quick. There's a picture of just a generic polar curve, r of theta, and we mark a little segment of that that's infinitesimal. We're going to call that ds. Then we're going to figure out how to express ds in terms of r and theta. So I can see that ds takes up a small angle, an infinitesimal angle that I'm going to call d theta. And ds can be broken down into components. One of those is the tangential component and one is the radial component, and those two things are perpendicular to each other. That tangential component is given by r d theta. So I'm just using the formula from geometry, s equals r theta, relating arc length to radius and subtended angle. What about the radial component? That's just a small change in r. So that's dr. So using the Pythagorean theorem, I find that ds squared is dr squared plus r d theta all squared. And I can square root both sides to get an expression for my infinitesimal arc contribution. And I'll go ahead and square the r d theta, and I get r squared d theta squared. Then I'm going to factor a d theta squared out of the interior of this square root. So that means my dr squared term is going to be a dr squared divided by d theta squared. And then my other term, just r squared, I've divided the d theta squared out of that. And when the d theta squared comes out of the square root, I get a d theta. Finally, dr squared divided by d theta squared, that's just dr d theta all squared. And then I have my r squared and then a d theta. It's also popular to write this in prime notation. Dr d theta, that's r prime of theta. I need to square that, add it to r squared, and then my differential quantity for theta, d theta at the end. So to get the total arc length, I just add up all these contributions. That's what integration does. So I have the integral of ds. And then I want to go from some starting value of theta to some finishing value of theta. So it'll be theta 1 to theta 2. And we've got our formula for the arc length of a polar curve. So like we've seen with other arc length formulas for rectangular coordinates and for parametric form, this is just such an ugly expression that it usually creates an integral that can't be done analytically. And that's the case for our example this time as well. I'm going to prep a little bit here by finding r prime. And that's a negative 4 sine 2 theta. But the chain rule requires me to multiply by 2 after that, so I end up with a negative 8 sine 2 theta. And now I can set up my integral. This entire rose curve is traced out once on the interval 0 to 2 pi. Be careful if you get a rose with an odd coefficient, by the way, because those are completely traced out on 0 to pi. You don't want to accidentally double count your arc length. But as long as the coefficient here is even, it's traced once on 0 to 2 pi. And the square of my derivative here is 64 sine squared 2 theta. And the square of r itself is 16 cosine squared 2 theta. So at this point, our integral is set up. And we're going to bounce to our computer algebra system. I'm using wxMaxima. It's a free and open source computer algebra system. And I've set up in here integrate. And then I typed in the square root of 16 cosine squared 2 theta plus 64 sine squared 2 theta. I just reversed the terms for some reason. And I'm integrating as t goes from 0 to 2 pi. Notice that percent pi is a special symbol for the number pi. And I hit shift enter. And when I do that, Maxima just tells me the integral over again. And this is Maxima's way of saying, I give up. I don't know how to do this analytically. So to get a numerical approximation, we use a different command. It's called quad QAG. And the quad QAG command gives you 6 different algorithms to choose from for how to numerically integrate this thing. And it's not going to make a difference for us which algorithm we choose. So I'm just going to choose algorithm number 1. So notice that when you use quad QAG, you have to have that extra argument for the command to make sense. And I'm going to hit shift enter. And the first number that pops out is the numerical estimate of the integral. The second number gives you an estimate of how much error is committed in that integral. So the error committed here is well beyond the place value that we're going to round to. In the problem, I was asked to round to the thousandths place, so it's 38.754. And we should probably verify that this makes some intuitive sense, that our number is at least in the ballpark. So what we could do is say the distance from here to here, I'm just splitting the top petal in half. The distance from the origin to the tip of that petal is 4 units. And each half of that petal is going to be more than 4 units to get to that tip because those are curved instead of straight. So as a lower bound here, the arc length of one petal has got to be bigger than 8, which means the arc length of 4 petals has to be bigger than 32. And I'm in the ballpark here, so we'll conclude that our answer is reasonable. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.